Okay. Yeah. Hello, everyone. I'm Irmak. I'm a PhD student at NYU. I'm advised by Lerrel Pinto, and majority of my research focused on learning, like robot learning applications for dexterous hands, robot hands. So today I will be talking to you about closing the human to robot gap for dexterous hands. So as a little bit of status quo in robot learning, we are seeing autonomous robot policies every day, more and more these days. And this is also another example of a robot policy being deployed to open the lid of this sauce container, like a very small sauce container. So given robot data, with the robot data, nowadays we are recipe for learning autonomous policies and deploying them in real world is getting better and better explored. This is also another example of a similar task, like on the similar robot environment where these robots are trying to pick up almost a transparent tape and then cut it forcefully and then insert it, like transfer that to the other robot and then insert it to a location, which requires pretty contact rich and pretty interaction heavy manipulation. So, what is this recipe that like enables these sort of behaviors? Currently, the recipe like that, that this paper was released 3 years ago, and ever since then, and also following up to that, this recipe has been very well explored. And it is to collect some robot data, somehow control the robot to complete tasks in a desired way, and then train policies to mimic those behaviors. So for grippers, this data collection, so like what you just saw before, like they are gripper robots, two-fingered gripper robots. Usually like robot data collection is slightly simpler because the control of these grippers are slightly like simpler as well. But for robot hands, this robot data collection has mostly has been done by teleoperating the robot. So what I mean by teleoperating is usually wearing some hardware, either a VR headset or some Aria glasses these days, like smart glasses these days, to extract the hand poses of the human and stream those hand poses to the robot somehow, and then extract joint angles to be applied on the robot, and then like stream the visual feedback of the robot back to the user. So for example, let's say that we have an app and system like this, where a human wears a VR headset. They move their hand accordingly to what they want the robot to do. Inside the app, they are seeing their hand pose, like extracted hand pose, and they're also seeing the visual stream of what the robot is doing. So in this way, like robots, like a users, as they're moving their hand, like as I said, they're seeing their hand and they can move the robot according to what the visual feedback like is coming from the robot. So in this system, like this was a paper that we released a few years ago, and at that time there were not a lot of reliable frameworks to collect demonstrations with dexterous hands. So yeah, like given a human and a robot setup that looks like this, with this app that like the system that we developed, the users were able to just like observe what the robot was doing while their hand pose is streamed to the robot hand. And this enabled data collection in 60 hertz, like a very reactive data collection in real world. So given that we have systems like this, we can just collect data on the collect data with the robot, and given observation action pairs, we can train policies, we can train models to mimic these behaviors, to apply the action that was like applied in a similar observation when we're deploying it. But even though we have these sort of reactive systems to collect data and then deploy policies on it, teleoperation still takes a significant amount of time. Like usually robot hands are very different than human hands. Their morphology is different. Their like the way they look is different. Their size is different. So user basically needs to constantly map how their hand is going to look like when it's retargeted on this huge hand, for example. As an example, these are just like visualizations of a human trying to teleoperate these like contact-rich tasks. Here on the left, a user is trying to teleoperate like to pick up like a clip, and on the right, user is trying to teleoperate the robot to sort of pick up this syringe in a functional manner, like a functionally grasp the syringe to potentially maybe do further manipulation. But as you can see, it is like really hard to actually like sort of know what to do and when to do and how to do it. So that's why recently there has been a lot of push towards somehow utilizing human data and adding that human data in this recipe for imitation learning. And by human data, what I mean is humans just directly completing the tasks themselves with their own hands instead of teleoperating the robot. And usual recipe so far has been collecting human data with similar hardware, some hardware that will give us human hand pose and head pose, like necessary annotations to extract actions from. Then we retarget that data to the robot. Usually, by what I mean by retargeting is to similarly replaying similar actions that a human does in the robot. But like like due to the differences, this is a whole branch of research on its own. And then after retargeting, we can train policies and that retargeted data. Some works does this like other way around. They train the policies directly on human data and then retarget to the robot. But like that seems to be the overall recipe that shows some promise. So the early examples of this approach is, for example, like um, in this project, they learned like affordances, general affordances from large scale human data, internet like a scale human data. And then they somehow retargeted those affordances to the robot directly. So that the robot, like given some general affordances, robot will be directly able to apply the actions. And these affordances look like grab it from here and then pull it towards here, open the door towards there, and etc. And similarly, like there are recently we also released a paper where we are trying to learn like a human actions that looks like this, for example, where the human just goes in and then picks up the eraser, and then we just like try to deploy it directly on the robot. And here, like we are tracking the objects and like visually tracking the objects with points, like they tracked the object with points to sort of like to remove the human hand and the robot hand from the system. But important thing here is like, for example, in these videos, the motion of the gripper of the way the human collects data is very specific to how they would collect it if their hands were grippers. So these these sort of measurements are taken to like enable this sort of retargeting for the robot so that the actions extracted from the human data can directly deploy on the robot. So when we're working with hands, though, okay, given affordances, apply actions, or given some like naive action priors, deployed on the robot. That part is slightly a little bit like more non-trivial because first, human hands are morphologically very different from robot hands. They're softer, they're smaller. There are so many more degrees of freedom on the human hand compared to the robot hand. And even if we do end up being able to train the robot, hands are visually very different as well. A robot hand looks, yeah, I mean, like they're very different. That they're usually black. There are so many differences visually with the human and the robot hands. So like the way I sort of like try to attempt different solutions is I asked two like I sort of like approach to this embodiment gap from two different sources. One of them is from algorithmic approach. Can we design algorithms so that we can close the human to robot embodiment gap by developing algorithms like in learning, like with data, or like, developing algorithms to learn policies from human data. And the other one is how can we even just close this embodiment gap with building better hardware by like, designing better, more humanoid and just like in general, more capable robot hands. So first, I want to start with the first part of it. So in this project, we present Hodor is the name of the project, and we are basically trying to retarget an open loop trajectory that a human does to complete a task to the robot. So here, as you can see, the way a human completes this task of like opening music box, the robot also opens the music box, but the robot's actions are significantly different than the human hand. As you can see, like relatively, when you look at the two hands, the way they move are significantly different. And yet they both manage to open the music box, which is, when you think about it, is the important thing that we want robots to do. We don't necessarily care how they move, like how they move, but we want them to complete tasks. So in Hudor, what we sort of like explored is to close this embodiment gap between human and robot with object-centric reinforcement learning. We extract object-centric rewards and then learn online reinforcement like agents to improve this base policy, which is basically just replay of the human demonstration. So like more in details, how this like a framework works is given some human rollout and a robot rollout. We track the points on the objects using some off-the-shelf vision models. So on the top, you can see that the music box, the human was able to open the music box, and on the bottom, you see that the robot was not able to open the music box. And we track each of for each of the rollouts, we track what happens to the music box using code tracker, like off-the-shelf vision models. So then by comparing how the points moved across these two different trajectories, we extract some deterministic reward. In this case, what we did is we compared the mean translation and rotation around a mean translation and rotation of the points, basically, and then compare them with the robot rollout one. And this provided somewhat dense reward, and we were able to learn a residual policy that would get added to the replay data. So like we have a human trajectory, and then we learn a residual trajectory with this policy, and then we just sum it up and we deploy that on the robot. So in this way, we were able to close the human to robot gap. So here are some example videos of these, like how our data looks like. So on the top row, you're seeing the human rollouts, and on the bottom, you're seeing the robot rollouts. Because we are learning a residual, each epoch, each episode has the same amount of steps, like because the robot just rolls out the human demo and then adds like a slight residual on top of it. So similarly here, so that was the music box opening task on a successful rollout. This is bread picking. There's a bread in the middle, and then we're just picking that up. The third one is sliding a piece of paper. And then the fourth one is picking up a card by sliding and picking up a card. And you can see like how the tracks look like as well. So we also, in order to explore how well policies trained with Hudor, like generalizes to new objects. Like let's say that we train the model in card sliding, like with a card, but then we want to deploy it with different objects, such as like gum package or tea bag or like plate and stuff like that. And we observed that because we are inputting the tracking points instead of images as input to our policy, um, it was able to generalize to objects like when the weight or the like thinness of the object significantly different than the original object, like the shape and the like at least like small differences in the shape or the color didn't really matter too much. But the tea bag is, for example, very light and the napkin was very thin. So when the action is significantly different than the trained object, then we would observe some failures. But as long as like it's only shape, a little bit of shape and um, color, we were able to perform relatively better. And this is also similarly generalization of bread picking on new, like on different objects. On this one as well, due to the lack of contact information in human data, when the objects are significantly different in weight or slippery, a slipperiness, like the red pug, that's a pretty slippery object. So it would always like slip from the hand. Whereas like when music box, picking up a music box, since the shape and the texture is like a little bit more similar, or doable with bread picking, like it was able to relatively perform better. And also, finally, since this is like a significantly, like it's a work that focuses significantly for retargeting from human demonstrations, it was learning a policy, a small policy on top of the human demonstration that was provided, like from a single human demonstration. So in order to enable some spatial generalizability, we added spatial generalizability experiments and we decoupled the arm deployment from the hand, where hand just runs the Hudor policy, whereas arm is moved relative to the initial object position. Like, I mean, depending on where the new object position is compared to the demonstrated object position. And then we move the arm that amount like relative to the initial arm pose as well. So like in this way, we were able to somewhat get spatial generalization for not too dexterous tasks like bread picking, whereas like for tasks that are kind of much more dexterous, like music box opening, success rate was like slightly lower across a 50 centimeter to 30 centimeter box. So yeah, this was Hudor, bridging the human to robot dexterity gap through object-oriented rewards. This is the card sliding task deployed on the robot. I think the major limitations of this work was having to do RL, reinforcement learning in real world was very difficult and like it would take like somewhat like an hour, for example, or 1 hour to retarget one task. And then the other limitation was using 2D object points makes this approach kind of prone to camera view and prone to just like quality of the trackers. So I think like either exploring maybe more robust approaches to enable 3D tracking or like sort of occlusion safe tracking. Like I think like those would help significantly with these sort of approaches. So the second part of what I want to talk about is how can we design better hardware? Like how can we actually close this embodiment gap with having better hardware? And so this is then we developed RUKA. This is a tendon-driven hand. I actually have RUKA next to me as well today. But yeah, like it's a tendon-driven hand. Um, it is open sourced, fully open sourced. Anyone can 3D print and build it. It like it used to take $1,300 when we released this paper. I think now with motors and etc., like it ends up being slightly more expensive. But yeah, like under $1,300. It took a completely new person to build from end to end 7 hours, like including the time spent looking for an Allen key in the lab and all that as well. It has 15 degrees of freedom, four of which is underactuated. The pip joints are underactuated. Um, so it has 11 motors on the wrist, and it is, as you can see, pretty anthropomorphic. While I'm moving my hand, the robot hand does the exact same, like similar motions to what my hand is doing, which sort of showcases the simplicity of the teleoperation system. And we're able to, yeah, just like live teleoperate it as we go. Okay. Um, so as the as like sort of the motivation, and again, like similar status quo of what was happening before RUKA. So nowadays, like we are seeing more and more hands everywhere. We're getting like there's new robot hardware being developed like significantly. But at the release of this paper, where we were at was we had very highly used Allegro hands, which are very large. The hands that I just showed you in the previous paper was Allegro hands. They're very large. They have been extensively used for research in the community, but like a lot of people struggled with how large they were. And they were also relatively expensive as well, like around 15K. Then Leap Hands came out. They were open sourced hands designed in at CMU. They were similarly sized, but they only costed like only 1K or 1500 or so. So that was like now like widely used. But both of these hands are direct driven, meaning they have motors in the joints, which makes them bulky and large, and sort of creates this morphological gap issue. On the other hand, there were a lot of tendon-driven hands around as well. The most widely used one was shadow hand, which is very expensive. Like they have pretty complicated sensors to enable control. So they had like they costed around $100,000. And with like small like whenever there is some sort of like breakage or something, like whenever it broke, it would take them a while to get it repaired and stuff like that. And like there are even more intense human-like hands clone where they're using very complex systems like control systems to control these hands. And like that branch can like goes pretty intense. Like you can get very anthropomorphic, but finding like a system where it's easy to use and reliable and cheap and open source was like a missing part. And that's what RUKA enabled at that time. We were like this, we designed robot hand, we made it open source, and we made it tendon driven to make it small. But with tendon driven comes some problems. And here I talk about them. So because like so first with tendon driven hands, the mapping from motor readings to joint angles is just simply non-trivial. It's unclear how we map motor values to the joint angles. So that's why in RUKA we utilize a data-driven approach for this. We put a motion capture glove at the back of the hand, and then autonomously just collected data. Here, we just randomly ask the hand to go to these motor positions and save the motor position and joint angle pairs. Joint angle readings are coming from the motion capture glove, and because this hand is humanoid, like these motion capture gloves also works on these hands, which is if we were to put them on an Allegro hand, they wouldn't be able to give us accurate readings. In order to sort of include sequential nature of tendons, as in given a desired fingertip position, where the tendon is coming from, like where the finger is coming from, impacts the action we should output in the setup. So that's why we're training a sequential model, inputting past desired fingertips, and then outputs the motor positions for each degree of freedom. So in this way, we were able to um, teleoperate this robot hand for like completing these sort of like a dexterous and strong tasks. So that was the sawing. Then we have a Nutella opening task where the RUKA just like opens the cap of a Nutella. These are teleoperated, by the way. These are not autonomous tasks, but what we teleoperate could potentially turn into a task as well. And this is just like sort of in-hand rotation of a screwdriver. And this is inserting a battery. Yeah, so this was RUKA. This is also like our arm with arm live teleoperation system. So like at that time, we like the major limitation of this work was lack of wrist and the fact that it relied on manus. Like there were like a this motion capture glove. Like for reliable calibration, reliance on manus would mean that people needed manus glove, which costs actually more than the hand itself, to train their controllers. So that's why we recently released RUKA V2 as well, and mostly we added a wrist. Like this wrist, it's again tendon driven, but it has two DOF wrist, ulnar and radial activation like with like different directions, and also yeah, like extension and flexion as well. Like we also added abduction, adduction, like more degrees of freedom, like so that like all the fingers can move like this, and we were able to sort of showcase tasks, like the like this calligraphy, for example. Even though the fingers are not moving here, like we sort of like showcase, I guess, how the hand is able to hold the brush, and all that. So yeah, that was my presentation, and I very much thank to all of my collaborators here, like at the Star Lab, and there are also many more people who are not in this picture, but yeah, so.